Hello. Yeah, I am here. I'm making this video to understand what is a compiler and what a compilation process does. Being a computer science student, we have to know our tools, what tools we are using, and how it exactly works. You know how to compile a program. Generally, in C programming language environment, where we press the command Alt F9 for compiling. It's not that easy. Internally, compilation process takes place. When you press Alt F9, the compilation process, what exactly the compilation process does, that we study in a subject called compiler design. First, let me explain you the history, the theory part, which is important for you to understand how the compiler has come into existence. Yeah. So now, first compiler was created or developed in the year 1950 for a Fortran language. Mainly motto of developing a compiler is softwares for early computers was written in assembly language. Now they want to have or they want to reuse the software on different CPUs such that the cost of writing a compiler may come down. That is the main motto. And making it that aspect, first compiler was created was Fortran and it has taken nearly 18 man years to build. Nowadays we can create a compiler within a 6 months. We can take it as a student project, mini project work, and we can finish build a compiler within a 6 months of time. That is the main thing. Yeah. So compiler design, we this subject has got a connectivity with automata theory. So what are the concepts that we have studied in automata theory are used in designing the compiler. First point is that, yeah. So what a compiler does, compiler acts as a translator where the human understandable language or the programming language, we call it as a source language, give it to a machine, converting or translating into machine understandable language. The language that we are writing, we call it as a source, and the output we call it as a target language or machine understandable language. Now this is source is the input that we are providing is a machine understandable language, sorry, human understandable language, whereas the output is a machine understandable language. So in between the translation of source language, human understandable language to machine understandable language, compiler is the one which will does the job. Apart from this, it will also report you errors if there are any in the source program. Okay. So again, yeah. So there are so many things there. This is the structure of a compiler. Any compiler must perform two major tasks. One is analysis and other is synthesis. So now compilation we seen broadly as one box. Now we have divided a compiler doing two major tasks. One is analysis of a program and other part is synthesis. So analysis is require synthesis require more sophisticated techniques than analysis part. Okay. Now this is how analysis and synthesis we take it as a phases of compiler. Okay, so the entire compilation process we have taken it like a phases of a compiler. First, initially a source program input is given to a first phase of compiler, which is a lexical analyzer, and then the output of a lexical analysis is a tokens. These tokens are taken as input to the second phase of a compiler, which is parser. And what this parser does is it will verify the source code that you write is matching with the programming language syntax or not. So parser is the one which will does that job, and the output of the parser is a parse tree, and this parse tree is given as input to the semantic analyzer, and the semantic analyzer what it does is it will create output of abstract syntax tree. An abstract syntax tree, the output produced by abstract syntax tree is given to intermediate representation, which is in between high level language representation and low level language representation. And what we got here is, after intermediate representation, if a compiler has got a optimizer phase, code optimizer phase, we say it's a optimizing compiler. Some compilers do have this phase and some compilers do not have. If compiler having this optimizer phase, we call it as a optimizing compiler. Now the intermediate representation is given to the optimizer, which will give you optimized IR, and this optimized intermediate representation will be given to the code generator, which is the final phase of the compiler, and generates the target machine code. Apart from this, there are two other phases of a compiler, which is a symbol table and error handler table. So symbol table is the one which will store all the attributes, data, and their corresponding information, their scope, their value is stored in a data structure called symbol table. And we have another phase called error handler. What it does is, the errors that are reported from each phase of the compiler will be stored and thrown to the user, so that there is an error at this line number, rectify it. Okay, all the errors which are come are stored in a table called error handler table. From this error handler table, errors are shown to the user. Okay, yeah. So now this is scanner is nothing but a lexical analyzer, which begins the analysis of the source program by reading the input character by character and grouping characters into individuals, words and symbols called tokens. So in order to do this, we use internally finite automata, which we studied in automata theory. Okay. So the prerequisite for this subject is automata theory, and you know what is a regular expression, what is a non-deterministic finite automata, what is DFA, and what is Lex. Okay. Now this, what is scanner does is, internally it uses the concept of DFA in identification of tokens. Okay. And then the second phase of a compiler, which is parser. Now parser, what it does is, it will identify or it will verify the source code is matching with the programming language syntax. So programming language syntax is given by a context-free grammar. So the parser reads tokens and groups them into units, and it verifies whether it's matching with the programming language syntax or not. If it matches, then a parse tree is generated, or else a parse tree is not generated. Okay. Next is semantic analyzer. So what is the semantic analyzer does is, it will check the semantics of the program. Let us take it. I am adding two numbers A and B. Now A is of type integer, B is of type character. So can I add an integer variable and a character variable? Okay. Is this possible? Is this feasible? That kind of semantic checking is done in a phase called semantic analyzer. Not only that, when we have initialized an array of size 5. Now when I try to enter more than 5 elements, then it will throw you an error called array out of bound. So semantic analyzer is the one which will does this job. Okay. So next is the intermediate representation. Intermediate representation is the one which is intermediate in between high level and low level. Okay. And then we have a code optimizer. Code optimizer, what it does is, improving the running time of a compiler can be done by using a phase called code optimization. We can improve the code by taking the best algorithm. Suppose instead of using bubble sort, we can replace the bubble sort algorithm by a quick sort algorithm for sorting n,000 numbers. Let us take it. Okay. And not only that, declaring variables, okay, making effective memory usage, all these aspects will be done, taken care in a phase called optimization. So code optimization can be done at 3 levels. We can optimize the code at source level, which is the program that you are writing. Optimization can be done at the intermediate code. Optimization then be done at a machine target code. So when you are doing optimization at the target code at a machine level, we say it's machine dependent optimization. And the optimization that you are doing at source level, at intermediate code level, we say it's machine independent optimization. We are not taking the aspects of machine internals like memory, RAM, secondary memory, cache memory. We are not taking all these accounts in. We do take care, or we do bother at target level only. Then optimizing at target level, taking memory and taking system internals. We say it's machine dependent optimization. Okay, and then finally we have a code generator. So we have so algorithms like how to generate a code generator, the target machine code. Okay, so these are all phases of a compiler. Now let us take it an example. We have a statement position equal to, now the source code that you are giving it to a compiler is position equal to initial plus rate into 6. This is the statement. Now what is this lexical analyzer does is, it will break down the program into smallest units and identify what are the keywords, what are the reserve words, what are the operators. Now position is a variable which is taken as identifier 1, and we have initial is identifier 2, and we have rate as identifier 3 into 60. This is the tokens that we got it output from the first phase of a compiler. Now second phase of a compiler, parser is, we have taken parser is, now from this generated we are going to draw a parse tree. Okay, so id equal to id1 equal to id2 plus first id2 plus id2 and plus id3 into 60. So now first id3 into 60 is performed, then the result is added to id2, and this entire result is stored in a identifier 1. So this is the parse tree that we are going to get it from the second phase of a compiler. And in third phase, abstract syntax tree means each and in detail of attributes are written here. For this same parse tree, we are decorating with attribute information. That is the reason we also call it as annotated parse tree. We call it as annotated parse tree. Okay. So what is this annotated parse tree is? Now here 60 means we are doing a conversion of integer to real. That is the thing in semantic analyzer. Now come to the code optimizer, intermediate code representation, which is intermediate code generated. What it is, at a time maximum 3 addresses can be used. Now id2 plus id3 into 60 cannot be done because there are more than 3 addresses. Now maximum 3 addresses means 2 for operating and storing in another. So we are creating a temporary variable called temporary1 and performing id3 into 60 and storing the result in a temporary variable 1. Now for this temporary variable 1 we are adding id3, and then what we are doing is we are doing id2 plus temp2, and then id1 we are storing the result that is stored in a temporary 3. This is about code intermediate code generator. Now come to the point of code optimization. So how we can reduce this 4 lines of code into 2 lines. So instead of directly writing it id3 into 60 as temporary variable, we will write id3 into 60 and perform and storing in a variable called temporary 1. Now this temporary 1 variable holds id3 into 60, directly adding id2 and storing in an identifier 1 is the optimization that we are going to do. Now finally target code. Target code we write it here in terms of machine code, assembly language code. So we take the value of id3 into storing in a register variable, and then performing into 60 in another register variable, and then id2 is storing in another register r1, and then finally adding r1 and r2 and moving r1 to id1. So this is entire process of compilation for a statement position equal to initial plus rate into 60. Fine, hope you understand.